Hey guys, this video is going to be about collision theory and reaction profiles. Collision theory is how the reactants have to collide in order for the reaction to proceed and what things can affect how fast the reaction occurs. So it describes the things that has to happen for a reaction to take place, and the things that you have to consider when you're thinking about this is how concentration affects the rates, how the temperature can affect the rate, and what other things could possibly affect how fast the reaction occurs. Okay, so we've looked at these before, but I just want to go over them again. The energy of activation. So for an exothermic reaction, the energy of activation is going to be right here from this line to the top of the peak, right? And that's for exothermic because our products have less energy than our reactants do, so that means overall the delta H of the reaction is going to be negative. We've lost heat. So we don't have to consider the energy of activation to be looking at that. And so the heat of the reaction, the enthalpy of the reaction that's given off is going to be right here. So it's where the reactants were to where the products end. And since it's losing it, it will be negative. All right, and then for an endothermic reaction, the energy of activation is going to be from where we start to the top of the peak. And then the delta H of the reaction for this one is going to be from the reactants up to the products. And so this one you can see is gaining heat, so it's positive, and it's going to be endothermic for that reaction. Okay, so another thing, the reactants have to have the correct orientation when they collide, or the reaction will not take place. So here's our reaction. Okay, we want A to react with BC to give us AB, and C gets let off. So if A were to hit C, then they would just bounce off of each other because A is not trying to react with C. A is trying to react. This would not help the reaction take place. A has to hit B so that A and B can form a compound together, and then C can be let go. So A has to collide with B. If the correct orientation of the reactants is not met during the collision, then the reaction can't proceed. So one of the requirements is correct orientation. So energy of activation has to be met. The reactants have to collide with the correct orientation for the reaction to actually go to completion. All right, so the reaction at different temperatures and how that affects the energy of activation. So if we look here in this first graph on the left, the number of molecules that have enough energy to overcome the energy of activation is seen under the curve. So for this reaction at temperature 2, because that line represents the second temperature, all of these molecules have enough energy to overcome the energy of activation. Whereas for temperature 1, it's a very, very, very small piece. There are not as many molecules at temperature 1 that have enough energy to overcome the energy of activation because it's at a lower temperature. So a higher temperature means that the curve kind of flattens a little bit out because more molecules have more energy. And so then we have the ability to react faster. All right. Now, if we add a catalyst to that reaction, so this is where a catalyst was added. What that does is it increases the number of molecules at that lower temperature that can overcome the energy of activation. All right, so this is our original reaction where we only have a little bit, right, of reactants that can overcome the energy of activation at that first temperature, right here. But when we add a catalyst, we have much more. Now, of course, that's going to affect the other one too. So it doesn't change the energy of activation, doesn't change the numerical amount. What it does is it changes how the reaction occurs and allows it to occur with a lower energy of activation, meaning that there's more chances for the reaction to occur in those collisions. All right, so The two requirements: the reacting molecules have to collide with enough energy to meet or exceed the energy of activation, and the orientation of the collisions has to be correct. So that's the basis of collision theory. And if we look at this equation right here, this is called the Arrhenius equation. So P is the steric factor, and that reflects the fraction of collisions with the correct orientation. Z is collision frequency, so how often they're colliding. And this little part right here is the fraction of collisions with sufficient energy, so the fraction of collisions that can meet or exceed the energy of activation. All right, and then we can rearrange this by taking the natural log of both sides of the equation, and we get this. And this is what you might see on the AP test. I haven't seen it in a really long time, but basically all it is the natural log of K versus 1 over T. So there's our Y, right? And then here's our X, 1 over T. And then we can get the energy of activation from the slope, where R is the universal gas constant of 8.314 joules per mole Kelvin. All right, so this is R. And so if we wanted to calculate the energy of activation using this right here, our slope, right, we would say, okay, M is going to be equal to negative E sub A over R. All right, so if I use my slope, negative 12,149 is equal to negative E sub A over 8.314. And I'm going to multiply both sides by negative 8.314 to get rid of that, to isolate the energy of activation. And I end up getting 101,007 joules. And so in kilojoules, or that's actually joules per mole, in kilojoules it would be 101 kilojoules because we just divide by 1,000. Honestly, though, I don't see this coming up. They could put it on there, but I really don't see it happening. All right, so that's it for this video. It's really straightforward. What you really have to know is this information. All right, and that's it.